Hello everyone. In this lecture we shall discuss the maxima and minima for function of several variables. Okay. Now if you recall a function of single variable, suppose y is equal to f of x, right? Now we say x is equal to a is a point of maxima or local maxima in the neighborhood of a. In the neighborhood of a. Neighborhood of a means in the locally a minus delta and a plus delta in this interval. If fa has the largest value, right, that means f of a is greater than f of a plus h. Similarly, if fa has the smallest value here, f of a is less than f a plus h, right. H may be positive or negative, but it is a very small number. Then fx attains the minima, right. And how to test the maxima and minima? We have the first derivative test and second derivative test. Here I will just recall you the second derivative test. Right, you are given a function y is equal to fx. For stationary point or extreme point, what you have to do? First derivative is equal to 0. F dash x is equal to 0. If you simplify it, you will get some say x is equal to x0 say. X is equal to x0 say. Now we say this x0 is a point of maxima, right? This x0 is a point of maxima if its second derivative is negative, right? If its second derivative is negative. And we say this is a x0 is a point of minima if f second derivative at x0 is positive, right? Now if the second derivative at x0 is equal to 0, then this x0 is a saddle point, right, or point of inflection. Point of inflection means fx doesn't have maxima or minima at x0, right, at x0. So this is the idea of maxima and minima for function of single variable. Now we will extend this concept for function of several variables, for 2 variables, for 3 variables, and in general for several variables. So before discussing these cases for the function of several variables, let me to introduce myself. Myself Professor Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra Sai University of Technology, Burla. As requested by many of my students, I plan myself to upload some video for the benefits of my students. And the beauty of this lecture is that the theory, basic theory with many solved examples are discussed for the easy understanding of the students. So without much delay, let us now extend the case of maxima minima for function of 2 variables, 3 variables, and so on for function of several variables. And now let us consider a function of 2 variables, f of xy, function of 2 variables, right? We say fxy has maxima. We say fxy has maxima or relative maxima, local maxima at AB, right? If f of AB is greater than f of a plus h, b plus k, right? Means in the neighborhood of AB, right? This f of AB is a extreme point, means it is a extreme value in the neighborhood of AB, right? Here h and k are small positive or negative number, right? As I have told you here, the neighborhood a minus delta, a plus delta. So we are taking minus delta and plus delta. Likewise, we have this h and k, right, may be positive or negative. So similarly, we can say that it attains the minima, right, minima means the relative minima at AB. If this FAB is the smallest value in this neighborhood, is smaller than f of a plus h b plus k, right. Here h and k are small number, small positive or negative number, right. So now this f of AB means f attains minimum value at the point AB, right. So this is the smallest value, right, and here f attains the maximum value at AB, right. F attains the maximum value means fxy at AB is larger than any value of f of xy, in the neighborhood of AB, right, in the neighborhood of AB. So just to recall that f of AB is greater than f of a plus h b plus k, and f of AB is less than f of a plus h and b plus k. Even greater than equal and less than equal is also allowed. And here f of xy at the point AB ensures the smallest value is less than f of xy, right, in the neighborhood of AB, right, in the neighborhood of AB. Now the test of maxima and minima. Test of maxima and minima. How to test this AB is a point of maxima or minima or a saddle point, we'll see. So what is the working rule? Now we consider the function of two variables. Consider f of xy. So at the first step is for stationary point, we have first derivative is equal to 0, right. Fx is equal to 0, fy is equal to 0. We solve simultaneously to get the point. Say, so after simplifying, suppose we get, say, x0 y0, x0 x1 y1, like that. Suppose, say, these are my points or anything else may be my points. Now we should go for the second derivative, right. Then we have to find the second derivative. We find fxx at the point x0 y0, right. Suppose you consider this point, then we find f of xy at this point x0 y0, then we find f of yy at this same point, the point what we are considering, right. And this point, as I have already told you earlier, this is my r, and this is my s, and this is my t, right. Now after getting the second derivative at x0 means we are testing at x0 y0. Similarly, we can go for the test at x1 y1, right. If here rt minus s square is positive and a negative and r negative, that means, what does it mean? That means the same thing as, that means here fxx into fyy minus f square xy is positive and your fxx is negative at this point at x0 y0. What does it mean? It means it is a point of maxima. It is a point of maxima there, right? It is a point of maxima. And for the point of minima, for minima, here rt minus s square is positive and r is positive. What does it mean? This is same thing as here fxx into fyy minus f square xy is positive and here fxx itself is positive, right? If this will happen, then we say that fxy attains minima at x0 y0 and f of x0 y0 is the minimum value of fxy, right? Minimum value of fxy. So to repeat, we consider the function f of xy. First we consider the first derivative. Partial derivatives is equal to 0. We find the stationary point. As many stationary points we may get, it is same as the less than equal to the degree of the equations. So now suppose I am considering this point. Similarly, as many as points we consider the individual points. Now for maxima here, we need this rt minus s square is positive as well as r is negative, and this is same thing as here this is same thing as this. We may write in this way or we may write in this way, right? Then we say that x0 y0 is a point of maxima and f of x0 y0 is the maximum value. And here for minima we have both are positive, right? And alternatively we may write it in this way. Instead of writing RST, we may directly write it like this, right? And both this and this is also positive, this is also positive, right? Then we say fxy attains the minimum value at x0 y0 and this minimum value of the function is fxy at x0 y0, right? Now you note that if here rt minus s square is negative, right, that means fxx into fyy minus f square xy is negative. If this is negative, then what will happen? Means we have the neither maxima nor minima, right? It is a saddle point. Then here x0 y0 is a saddle point. That means f of xy attains neither maxima nor minima at x0 y0. Now when this is here exactly 0, if here rt minus s square is equal to 0 here, then what will happen? Then no conclusion. Further analysis is needed. Further analysis is required. So you see here, in both the cases you see, in both the cases we have considered this is positive here also. For minima also we have considered this is positive. For maxima also we have considered this is positive. Means here the negative case and equality case, right, we have not considered for maxima and minima. We overlook these two cases here. However, we should point out what is a saddle point, right? We should point out what is a saddle point. Now let us discuss some examples, then your idea will clear. Before that, let me to tell you the working rule for function of 3 variables or several variables. Suppose we are extending it to for function of several variables. Let us consider a function of 3 variables, x1, x2, x3. I am considering a function of 3 variables. Now what I have to do? As usual, the first derivative test is common, means your fx1 is equal to 0, your fx2 is equal to 0, and your fx3 is equal to 0, fx3 is equal to 0, right? Means your fx1 is equal to fx2 is equal to fx3, first derivative is equal to 0, and we solve it simultaneously, to get the point, stationary point, say x0, y0, z0. z0 is a stationary point. Similarly, we may have another point x1, y1, z1. We may have x1, x2, x1, y1, z1. We have another stationary point, and similarly we may have x2, y2, z2. We may have another stationary point. So at each point we have to go for the test. Then we have to find the Hessian matrix. As I have told you, Hessian matrix. What is my Hessian matrix here? Now my Hessian matrix H is, we will consider the second derivative, f x1 x1, then f x1 x2, f x1 x3, then f x2 x1, f x2 x2, f x2 x3, and your f x3 x1, f x3 x2, f x3 x3, right? We consider this Hessian matrix, right? So, or in short I may write it f11, f12, f13, f21, f22, f23, f31, f32, f33. This is my Hessian matrix. So what do you mean by f? Suppose I say f13. What does it mean? It is f x1 x3. Means we partially differentiate del by del x3, del f by del x1. We first differentiate it with respect to x1, then with respect to x3. Means your del square f by del x1 del x3, in that way. Okay, so we have the Hessian matrix. Then we consider the principal minors. Okay, then we consider the principal minors. The principal minors, this will be my d1. So my d1 is my f11. Now what is my d2? d2 means we have a second order matrix keeping the diagonal fixed. So my d2 will be the determinant of f11, f12, f21, f22. Okay, and for my d3, it is the determinant of the Hessian matrix itself. It is the determinant, means we have the diagonal fix, right? We have the determinant of the Hessian matrix. So that will be my determinant of the entire matrix, f11, f12, f13, f21, f22, f23, f31, f32, f33, f32, f33. We take the determinant of this matrix. Okay, so similarly we can extend it to more variables. Now for maxima we should have, you see, for maxima what will happen here? d1 is negative, d2 is positive, d3 is negative, right? It is negative, positive, negative, starting with negative, right? And this one has to be positive always, right? This d2 has to be positive always. As I have told you in the previous case, rt minus s square is positive in both the cases. Okay, so this has to be positive in all the cases, whether it is maxima or minima. And for your minima, we have all are positive, d1 positive, d2 positive, and d3 positive. All are positive, right? All are positive, right? In case your d2 is, in a note we may see that if d2 is negative, then what will happen? This will lead to neither maxima nor minima. Neither means we are considering this D1, D2, D3 at this point. All are at a point. Suppose I am considering the point x0, y0 and z0. At a point, any point we take x0, y0, z0. Similarly, we can extend to all other points. It is x0, y0 and z0. At individual points we have to test. At the point x0, y0 and z0 means we are considering the maxima at a particular point. At a point x0, y0 and z0. Similarly, all other points will check, right? So for maxima we have alternatively negative, positive and negative. It is called negative definite. Negative definite. For maxima we have the negative definite for maxima, and all are positive, and this is called your positive definite. It is called positive definite, right? And it leads to your positive definite. It leads to your minima, right? Now the moment this D2 is negative, then it leads to a saddle point. Saddle point, right? Saddle point. Now this same technique can be extended to further variables, 4 variables, 5 variables, in general for n variables, and as a special case of this we can review our case of the second variable, right? So in another remark, you see we have considered f of xy. Already we done it. Now for this f of xy we have the Hessian matrix will be what? fxx, fxy, fyx, fyy, is not it? So this is my Hessian matrix, or I can write it f11, f12, f21, f22, is not it? Or I can denote it, this is my R, this is my S, and this is my T. This is my T. So as I have told you, so what is my D1 here? My D1 is fxx. Suppose at I am taking a particular point, I am taking x0, y0. At x0, y0, right? What is my D1 and what is my D2? My D2 itself is this determinant of fxx, fxy, fyx, fyy. Is it not my fxx into fyy minus fxy square? So here fxy is same as fyx under the continuity of the function. So is it not your same thing as here rt minus s square, right? So what we are getting? For maxima, what we are getting here? Fxx is negative, right? And here rt minus s square is positive, right? Is it not the same thing as d1 is negative and d2 is positive, right? And similarly for your minima, here both are positive. Here d1 is positive and d2 is positive. Is it not the same thing as here fxx is positive and here rt minus s square is positive, right? So this is a general rule, right? This is a general rule for maxima and minima for as many as variables may be. Okay. So in general, if you are given a function of n variables x1, x2, xn, then we have the Hessian matrix f11, f12, f1n, f21, f22, f2n, and fn1, fn2, fnn. Okay, we consider the Hessian matrix. Then for maxima you have d1 negative, d2 positive, d3 negative, d4 positive, and so on, right? This, and for minima you have here all are positive, d1 positive, d2 positive, d3 positive, all are positive, and this for maxima case it is called negative definite. For minima case it is called positive definite, right? This here also this greater than sign can also be replaced by greater than equal sign, and here also greater than sign can also be replaced by greater than equal sign, right? Greater than equal sign, and it is called positive semi definite. semi definite, right? Similarly here this less than equal sign may be less than sign may be less than equal to 0, and in this case we call, if less than is replaced by less than equal to, right, greater than is replaced by greater than equal to, then it is called negative semi definite, right? So similarly we can extend it to the case of the n variables, but at your level this up to 3 variables is enough. So let us consider some solved examples, then your idea will clear. Suppose you have one example, find the extreme values. Extreme values means maxima is also extreme value, minima is also extreme value of the function this, right? So now this is a function of two variables x and y, and we solve it. Coming to the solution, we first consider a first derivative. What is your f of x? F of x is 3x square minus 3, it is equal to 0. And your f of y we differentiate with respect to y, it is 3y square minus 12 is equal to 0. If we solve it, your x square minus 1 is equal to 0 implies your x is equal to plus and minus 1. X is your plus and minus 1. And if you solve it, y square minus 4 is equal to 0 implies y is equal to plus and minus 2, right? So since we are solving these two simultaneously, right, so we are considering the points, all points here, means it is, so simultaneously we consider the points. So what are the stationary points? For 1 we have 2, for 1 we have minus 2, and for minus 1 we have 2, for minus 1 we have minus 2. So these are all the stationary points, right? So these are the stationary points, okay, the stationary points. Now we would see, we verify the condition at each stationary points, right? At individual stationary points we will verify that rt minus s square, and accordingly we will decide whether it is maxima or minima or a saddle point. So let me to solve it in a tabular form, right, so that we can simultaneously study the behavior of all the points, the behavior of the function at all the points. Let us now find the second derivative. What is fxx? Fxx is the second derivative of this is your 6x. What is fxy? And it is same thing as fyx. So we differentiate fx with respect to y, it is 0, and fy with respect to x, it is also 0, right? And it is your 0 irrespective of any points. Then your fyy, we differentiate it with respect to y again. So derivative of 3y square is your 6y, right? This is your 6y, and we may say it my r, we may say it this is my s, we may say it this is my t. So now in the tabular form we check the rt minus s square at individual points. So now you see r at 1 2 point, x is 1, y is 2, so it is 6, means it is positive, right? At 1 minus 2 point, it is also 6, it is positive. At minus 1 and 2, it is 6 into minus 1, minus 6 is negative, and it is also minus 6. So we get it is negative, right? Now you come to your point s. S is 0 throughout, it is everywhere, it is 0 irrespective of any point, it is 0. Coming to your t is 6y at the point 1 2, means it is 12, it is 6 into 2, 6 into 2, it is 12, right? Then it is minus 12, then it is 12, it is minus 12. One more thing we have to find, rt minus s square, we have to find one more, we have to find rt minus s square, right? One more thing you have to find, your rt minus s square, So you multiply r into t, 72, it is positive. Then here you calculate, it is minus 72, it is negative. It is minus 72, it is negative. It is 72, right? It is 72, it is positive, right? Then what is your conclusion now? Coming to the conclusion. You see here, in first case, here r positive and rt minus s square positive, both positive. So it is a point of minima. And it is positive and it is negative, right? So you see, if this is negative, irrespective of this point, then it is a case of the saddle point. Right? Then you see, it is negative and it is negative. We don't bother. If this is negative, rt minus s square is negative, then it is also a saddle point. Then you see, this is negative and positive, right? Negative oppositely, negative positive, then it will lead to your minima, right? It will lead to your maxima, right? It will lead to your maxima. So what is the maximum value of fxy and what is the minimum value of fxy? So maximum value of fxy means fxy at the point is fxy at the point -1 and -2. Originally you're given f is this, right? You substitute this value, right? It will give you -1 -8 plus 3 plus 24 plus 20. It will give you 38. So this is the maximum value of fxy. And what is the minimum value of fxy? It is at the point xy. The minimum value is at the point 1, 2, right? You substitute 1, 2 and it will be your f of 1, 2, right? F of 1, 2 will be equal to, and this is my f of -1 -2 is this here. Now f of 1, 2 will be, you substitute here, it is 1 plus 8 minus 3 minus 24 plus 20. This will be your 2. So this is the minimum value and these are the extreme values. Okay, whether it is a maximum value or minimum value, these are all extreme values. And this is a saddle point and this is a saddle point. Okay, accordingly you should write. Coming to one more example where some complexity in solving this simultaneous case. Okay, so let me to solve one more example to have your idea clear. Let it be my 1, let it be my equation 1, let it be my equation 2. Now from equation 1, your xq is equal to x minus y, right? Now you substitute in 2. From 2 your x minus y is xq. Your xq plus yq is equal to 0. You have your factorization formula. So this implies x plus y into x square minus xy plus y square is equal to 0. So that means x plus y is equal to 0 or x square minus xy plus y square is equal to 0. So this implies here, from this you have y is equal to minus x. Okay, and here let it be silent, x square minus xy plus y square is equal to 0. Let it be silent. Now we consider this, y is equal to minus x. Now we substitute this in 1, right? Y is equal to minus x in 1. Now 1 follows your xq. 1 follows xq minus 2x is equal to 0 or x into x minus 2 is equal to 0. So this implies x into x square minus 2 is equal to 0. So this implies x is equal to 0, or this will give you x is equal to plus and minus root 2. So we are getting 3 values of x. Now let us see the values of y. So what is y? Your y is here minus x. So that means your y is equal to 0 and y is equal to your minus root 2 and plus root 2. Now simultaneously we consider these points. Okay. So what are the points here? Thus the stationary points. Thus the stationary points are 0 and 0. You should keep in this mind. So when this is root 2, this is minus root 2. When this is minus root 2, this is plus root 2. And when this is plus root 2 and it is minus root 2. So these are the stationary points. Now we see the behavior of rt minus s square. Now we find the second derivative. Okay. So what is my fxx now? We find fxx. One more thing. We have to also think of this also. One more thing, for additional stationary points we have to also think of this. Again you have x square minus xy plus y square is equal to 0. So your x into x minus y plus y square is equal to 0. But your x minus y is your x cube. You see here. So this implies your x into x cube plus y square is equal to 0 implies x fourth plus y square is equal to 0. You see, this is also positive and this is also positive, but this is giving 0, means you will not get any real value. We will get the complex value, right? Which doesn't give you any real value, which has no real value, right? But we are talking about the real values. So we have, these are the stationary points here, right? Now what is my r? Now my r is equal to fxx, s is equal to my fxy, and t is equal to my fyy, right? And we will tabulate them now. So now we have the second derivative of this. Okay, the second derivative of this. If we find the fxx, it will be 12x square minus 4. Accordingly, I have written here fxx, fxy and fyy. Now at the 0, 0 point, this will give you minus 4, right? This will give you 20, this will give you 20, and it is your positive, it is your positive, it is negative. Now s is 4, it is throughout, it is 4. Now what is t? You substitute the point, it is your minus 4, and if you substitute it, it will give you 20, and if you substitute it over here, it will also give you 20. But we need here rt minus s square, r into t minus s square. So this will give you 0. R into t, 16 minus 16 is 0. Okay, and this will give you 384, it is positive, and this will give you 384, this will positive, right? So you see, this is positive and this is positive. Now it will lead you to minima, right? Minima. And this is positive and this is positive, it will lead you to minima. But rt minus s square being 0, so this will give you, right? Here we cannot conclude anything, we cannot conclude, no conclusion at this moment, no conclusion, right? No conclusion. So what is my minima point here? Thus minimum value, hence minimum value of fxy is f of root 2 minus root 2, which is same thing as f of minus root 2 plus root 2. If you substitute it, it will be your minus 8. Okay, so this is the answer here. Now let us discuss a case of 3 variables. So you are given another problem, the behavior of the function at origin. Okay, at origin. So let us now see whether origin is a stationary point or not. So what is fx here? You differentiate it, it is 4x cube minus 2xz. It is actually y square z square. Okay, it is 4x cube. So this will give you 0. This is plus yz. This will give you minus 2x. Similarly, here fy is equal to minus 2yz square plus xz minus 4y. Similarly, here fz will be minus 2y square z plus xy minus 2z. So now if fx is equal to fy is equal to fz is equal to 0, if you solve them simultaneously, all will agreed when x is equal to, this implies x is equal to y is equal to z is equal to 0, right? So therefore the stationary point is, thus the stationary point is 0, 0 and 0. This is the origin. Now we have to think of the Hessian matrix. What is my Hessian matrix now? Here H will be fxx, fxy, fxz, fyx, fyy, fyz, fzx, fzy, fzz, right? This is the matrix at the point origin. If you simplify it, here fxx will be 12x square minus 2. At 0 it is minus 2. So this will be my minus 2. Accordingly this is 0 and this is 0. This is 0, minus 4 and 0. This is 0, 0 and minus 2. Then we think of the principal minors. Okay. What about your d1? d1 is minus 2. It is negative. What about d2? You take the determinant of this. It is minus 2, 0, 0, minus 4. Okay. You take this determinant. So this is equal to 8 is your positive here. And what about your d3? d3 is the entire determinant, minus 2, 0, 0, 0, minus 4, 0, 0, 0, minus 2. It is a diagonal matrix. So this determinant value is the product of this diagonal. It is here 4, 2, 8 to 16. It is minus 16 is your negative. Okay. So alternatively negative, then positive, then negative. So that means 0, 0, 0 is a point of maxima, right? It is negative definite. So 0, 0, 0 is a point of maxima. And what is the maximum value? And f of 0, 0, 0, if you substitute x0, y0 and z0 in this equation, then it is 0. So this is the 0 here, right? This is the extreme value, right? Now let us solve just one more example. Suppose you are given one more question. Discuss the behavior of the function. So what is fx1? fx1 is 2x2 plus 2x3, and here fx2 is 2x1 plus 2x3, and here fx3 is, if you differentiate with respect to x3, it is 2x2 plus 2x1. Okay. Now if you solve them simultaneously, fx1 is equal to fx2 is equal to fx3 is equal to 0. So if all are simultaneously 0, only when here x1, x2, x3 is equal to 0, 0, 0. So this is a saddle point, right? This is a saddle point. Now you find what is f11 here, fx1, x1, or f11 here. f11 here is, here f11 here is 0, right? And here what is f12? f12 is 2. f13 is also 2. Accordingly here, so accordingly we have these values. Now what is the Hessian matrix? Hessian matrix is 0, 2, 2, 2, 0, 2 and 2, 2, 0. So this is my Hessian matrix. Now what about the principal minors here? d1 is here 0 here. And what is d2? d2 is the determinant of 0, 2, 2, 0. So this is my minus 4 is negative, since this is negative. So 0, 0, 0. Thus 0, 0, 0 is a saddle point, right? Is a saddle point, right? The video is getting lengthy, so we should close here, right? So this is the way to find the maxima and minima. Means the principle is you first consider the given function and you consider the first derivative with respect to all the variables and equate them to 0 simultaneously. This is called the necessary condition, and simultaneously solve it to find the your extreme point, or what you call the your stationary point. So at individual stationary points you go for the test rt minus s square, right? And accordingly you decide it is maxima or minima or it is a saddle point, or in general for function of several variables you take the Hessian matrix and you find the principal minors at the point at all the stationary points, and accordingly if all the principal minors are positive it will lead you to minima, and it is alternatively negative positive so on. And be sure that second one is always positive, d2 is always positive, otherwise it will lead to a saddle point. Okay, so accordingly you decide whether it is maxima or minima. In our subsequent lecture we will discuss the Lagrange multiplier, and it is also the way to get the maxima and minima where with this given function some additional relation is given. Okay, we will discuss it in our next video, next lecture. So now if you find this lecture is interesting and helpful, you should subscribe to this channel, which will boost my motivation and which will help me to upload the subsequent video for your benefits. Okay, thank you then. Have a nice day. Thank you all once again.